Welcome to Chapter 1, Section 5, the Extended Real Number System. This is a short but important section where we extend the real numbers by adding two new symbols, plus infinity and minus infinity. This extension is not about creating new numbers in the algebraic sense, but about providing a convenient framework so that expressions like the supremum of an unbounded set always make sense. Here is our outline for this section. We will start with the motivation for extending the real number system, then state the formal definition, look at a diagram of the extended real line, discuss the consequences for suprema and infima, go through the arithmetic conventions, and wrap up with a summary. Before we state the definition, let's understand why this extension is useful. In the real number system, if a set is not bounded above, then it simply has no supremum. For example, the set of all positive integers has no least upper bound in the reals. This is inconvenient because we often want to write expressions involving suprema without first checking whether the set is bounded. So what do we really want? The goal is to set up a system where every non-empty subset has both a least upper bound and a greatest lower bound. This makes many statements in analysis cleaner and avoids endless case distinctions about whether a set is bounded or not. How can we achieve this? The solution is elegant and simple. We adjoin two new symbols, plus infinity and minus infinity, to the real line. These are not real numbers and do not obey all the field axioms, but they give us a convenient extended system. Let's see the formal definition. Here is definition 1.23. The extended real number system is the real field R together with two new symbols, plus infinity and minus infinity. We keep the original ordering among the real numbers exactly as before, and we declare that minus infinity is less than every real number, and every real number is less than plus infinity. So minus infinity is the smallest element, and plus infinity is the largest element in this extended system. This diagram shows the extended real line. The real numbers sit in the middle, just as before. At the far left, we have minus infinity, and at the far right, we have plus infinity, shown with open circles to emphasize that these are not actual real numbers. They are symbols that we adjoin to the real line purely for convenience. The key point is that the ordering is total. Every element is comparable to every other element. Now let's see the immediate payoff of this extension. Since plus infinity is greater than every real number and also greater than minus infinity, it is an upper bound of every subset of the extended real number system. What does that imply? Because plus infinity serves as a universal upper bound, every non-empty subset is guaranteed to be bounded above, and hence has a least upper bound in the extended system. This is a powerful simplification. We never have to check boundedness before taking a supremum. And of course, the same idea works in the other direction as well. By exactly the same reasoning, minus infinity is a lower bound of every subset. So every non-empty subset also has a greatest lower bound, or infimum. Together, these two facts mean that suprema and infima always exist in the extended real number system. Let's see what this looks like in a concrete example. Here is the key example. Suppose E is a non-empty set of real numbers that is not bounded above in R. In the ordinary real number system, the supremum simply does not exist, but in the extended system, we simply say the supremum of E is plus infinity. Similarly, if E is not bounded below, then the infimum of E is minus infinity. This convention lets us write suprema and infima without ever worrying about boundedness. Now let's turn to the arithmetic conventions for the extended reals. Before we list the arithmetic conventions, an important warning. The extended real number system is not a field. You cannot do arbitrary arithmetic with plus and minus infinity. Expressions like infinity minus infinity, 0 times infinity, or infinity divided by infinity are left undefined. They are indeterminate forms that you may have encountered in calculus. Despite this, there are several useful conventions for operations that do make sense. Let's go through them one by one. Convention A applies when x is any real number. Adding plus infinity to x gives plus infinity. Subtracting infinity from x gives minus infinity. And dividing any real number x by plus or minus infinity gives 0. These make intuitive sense. No finite number can affect infinity by addition, and dividing a finite quantity by something infinitely large gives 0. Next, let's see what happens with multiplication. Convention B tells us what happens when we multiply a positive real number by infinity. A positive number times plus infinity is plus infinity, and a positive number times minus infinity is minus infinity. The sign is preserved because a positive scaling factor does not change direction. What if x is negative instead? Convention C handles the case when x is negative. A negative number times plus infinity is minus infinity, and a negative number times minus infinity is plus infinity. The sign flips, just as it does for ordinary multiplication by a negative number. Notice that the case x equals 0 is deliberately excluded from both B and C. The expression 0 times infinity is undefined, as it is an indeterminate form. Before we wrap up, a quick note on terminology. When we want to distinguish ordinary real numbers from plus or minus infinity, we call the real numbers finite. So saying x is finite simply means x belongs to R. The diagram shows this. The extended real number system is the big box containing both the finite reals in the middle and the two infinite symbols on the outside. You will see this terminology used frequently throughout the rest of the book. Now, let's summarize what we have learned. Let's review the key points from this section. First, the extended real number system is simply the real numbers, together with two adjoined symbols, plus infinity and minus infinity. The ordering places minus infinity below everything and plus infinity above everything. The main benefit is that every non-empty subset now has both a least upper bound and a greatest lower bound. We never have to worry about boundedness when writing suprema or infima. This is the whole reason we introduced the extension. However, this convenience comes with a caveat. The extended system is not a field. We cannot do arbitrary arithmetic with plus and minus infinity. Expressions like infinity minus infinity, 0 times infinity, and infinity divided by infinity are left deliberately undefined because they are indeterminate forms. Finally, we have the three arithmetic conventions for combining real numbers with infinity. These will be used throughout the book whenever we work with limits, suprema, infima, and series. In the next section, we will extend the real numbers in a completely different direction. Instead of adding infinite elements, we will add a square root of -1 and build the complex number field.